Welcome to ERC TipsKnowLogy. This is the third series of the Zener diode calculations discussion. So, taking it from part 2, we have another example here where in the previous example, we will have to change the 20 volts to 30 volts for the value of the voltage DC input. And the question is it safe, or is the IZ that we will get in this circuit will be safe? As you can see in the circuit, we have an 82 ohm RS, we have a 9 volts VZ, we have RL 100 ohms, and we have VDC in, which is 30 volts DC. Take note that the current coming from the voltage input is called I total or IT, and the current going through the RS is called IRS or IS, and IT is also equal to IS. And at this point, we will be having IL, which if we add it to IZ, will be giving us the IT. So in the previous examples, we learned how to calculate the IL, and that is by dividing the VZ divided by 100 ohms or RL. And take note that VL is equal to VZ because the VZ will be equal to VL because they are in parallel. And when we divide 9 volts divided by 100 ohms, the answer will be 0.09 amperes or 90 milliamperes. And for I total, by Ohm's law again, the V over R will become Vs over Rs. And this Vs is the voltage that we have on the RS. So if we get the VRS, that will be the sum, the subtraction of VDC in minus the VZ. So VDC in minus VZ divided by 82 ohms, which is the RS, will give us 256.098 milliampere. Take note that when you are dividing volt by ohm, the answer will be ampere. And to get milliampere, you have to multiply this value by 1000 because there's 1000 milliampere in every 1 ampere. So 1000 milliamperes for 1 ampere. For IZ, we subtract IL from IT and we got 256.098 milliamperes minus 90 milliamperes. We get 166.098 milliampere, which is greater than the IZ max, which is 55.5556 milliampere. Therefore, the Zener diode will be very unsafe. Now, suppose that the uh, VDC in changes from 20 volts to 18 volts. What will happen to our diode? Will it be safe? Will IZ be safe? So if that's the case, that the 20 volts before in the VDC in, we made it 30 and then it's not safe. Now let's try to make it lower than 20. So let's say 18. And when we do that, we have IL equal to 90 milliamperes and the IT becomes 109.756. So if we calculate for IZ, it will be 109.756 milliamperes for IT minus 90 milliamperes for IL. We will be getting 19.756 milliamperes, and this will be less than the IZ max, which is 55. So we can say that the Zener diode is safe. Again, to summarize this, we have to calculate IL and IT so that we can get the IZ. After getting the IZ, you have to compare it with the given IZ max, which is 55.5556. We got this IZM from previous examples, and we are just continuing our discussion about it. Now, if the IZ is less than IZ max, then the Zener will be safe. Now, what if a Zener diode, particularly 1N754A diode, has a DC power dissipation rating? So this is the power of that Zener diode, 500 milliwatts. And it has a nominal Zener voltage of 6.8 volts. What is the value of IZ max for the device? So to solve this problem, we can see that the PD max is 500 milliwatts and the VZ is 6.8 volts. So what is the IZM? So we will use the formula power is equal to VI, and from P equals VI, we can get the formula I equals P over V. Therefore, the IZM or the IZ max, Zener maximum voltage, will be equal to the PD max or the maximum power dissipated by that Zener diode divided by the Zener voltage. So PD max over VZ, we will have 500 milliwatts divided by 6.8 volts. And of course, because this is milliwatts, the answer will be milliampere. It's important to write the unit after calculating the IZM. If you want to make this amperes, you have to divide it by 1000, and this will be 0.0735294 amperes. Now, in the slide, we have here IZM equals PD max over VZ. It's the same with what I have done here, but what I did is just to show you that the power can be calculated by VI and the I will be equal to P over V. Now, just to continue, assume that you have again, the 10 volt Zener diode, and it can maintain a volt regulation over currents IZK to IZM. And we have to find the V in minimum, and we have to find also the V in maximum. So let's check the battery first. Okay, so just to continue with what I am discussing about. So in this circuit, you will see that the Zener diode used was 1N4740, and it has no load resistance here. So the IZK, the minimum Zener current, is given as 0.25 milliamperes, and the PD max or the maximum power dissipated by the Zener diode is equal to 1 watt, and the Zener voltage is 10 volts. So we will find the minimum V in and the maximum V in. That is the voltage necessary here in order to provide the 10 volts regulated voltage output. Again, if we give this V in minimum here, the voltage will be 10 volts. And if we give up to the maximum V in, it will still be 10 volts. That's the idea behind it. What will be the minimum voltage input and the maximum voltage input that will be best to produce this regulated voltage of 10 volts. And to solve that by using the power formula, P equals VI, we got I is equal to P over V. Therefore, the IZM will be equal to P over V, which is PD max over the VZ, which is 10 volts. So PD max is 1 watt divided by 10 volts. So we got zero point 0.1 ampere. Take note that when you divide watt or watts divided by volt or volts, the answer will be ampere or amperes. And if you want to change it to milliampere, you only need to multiply it by 1000. So it will be 100 milliampere. So in our calculation, the IZM is equal to 100 milliamperes. And from there, we will use the formula Ohm's law, where the voltage is equal to the product of the current and the resistance. So V equals IR. If we want to get the V of the R minimum or the VR minimum, we have to multiply the IZ by the R. And the IZ minimum will give us the VR minimum, because the IZ is minimum multiplied by R. of course, the VR will be minimum. On the other hand, if you multiply IZ maximum to the R, we will get VR maximum. But take note that we are trying to calculate first for the VR minimum, or the minimum voltage on the resistor here. And remember, the current that will flow here will be the IZK, because when we say IZ minimum, it's the same as IZK. Remember from the previous discussion, the IZK and IZ minimum have equal values. So we can put the value 0.25 milliamperes from IZK and multiply it by our 220 ohms R. And we will be getting, of course, millivolts. So the milliamperes multiplied to ohms will be millivolt. So we have 55 millivolts here for our VR minimum. Therefore, the VR minimum is equal to 0.055 volts if you want to use volts, or you may also write it as 55 millivolt. Take note that the letter M must be written in small letter. If you wrote it in as a big letter, then it will be signifying like it's a mega. Now, the input voltage here, V in minimum, will be equal to VR minimum plus VZ. And the VR minimum is equal, again, as I have calculated here, equal to 0.055 volt. Therefore, if you add 0.055 volt plus 10 volts, the answer will be 10.055 volts. That will be our V in minimum, 10.055 volts. And the V in maximum, therefore, will be the VR maximum plus VZ or VZ. So in this circuit, the voltage input is equal to the sum of the voltage on the VR or VR plus the Zener voltage here, which is 10 volts. So if you have a minimum VR, the V in minimum will also be minimum, or the V in will be minimum. But if your VR is maximum, your V in will be maximum. So that's it. We have found the V in minimum and we found the V in maximum as well. And that's equal to 10 volts approximately. Our V in must be between 10.055 volts up to a maximum of 32 volts to make sure that the Zener diode will be operating normally, or it will be safe to produce the 10 volts output voltage. Take note also that this has no load resistance here. Now, this example, we will be determining the network or the circuit to find the range of RL and the range of IL to maintain VRL at 10 volts while the input voltage is 50 volts. In other words, the input voltage here, V in DC, will be equal to 50 volts DC. And we are trying to find the load resistor that will be between a minimum value to a maximum value, and also the IL minimum and the IL maximum in order to produce a voltage VRL of 10 volts. Now, the given Zener voltage is equal to 10 volts. And of course, we are expecting that an almost constant 10 volts will be going on the output, which will be parallel to the RL. And the IZ maximum here, or IZM, big letter M here, is equal to 32 milliamperes. Therefore, the given here is assumed to be 10 volts Zener voltage and 32 milliamperes IZ maximum. And we have the resistor here, which we can call as R or RS as 1 kilo ohm. Now, in the calculation solution, the diode will be on only if the RL minimum is equal to RVZ divided by VI minus VZ, and by substitution we will be getting 250 ohms. Of course, this is not clear because the exact calculations and substitution of values were not shown, but don't worry, I will be showing it to you after this slide. And after we calculate the RL min, which is 250 ohm, we may also calculate the VR, or the voltage on the resistor series with our voltage input. And that is possible by subtracting VZ from V in, or VI, which is also our V input, minus the Zener voltage, and we will be getting 40 volts. Again, the exact substitution of the values were not shown, but I'll be showing it to you to the next slide. Let's just go ahead on the discussion, and the IR can be taken by dividing R from VR. So the current on the resistor R will be equal to the voltage on the resistor R divided by the resistance of that R. And we will be getting 40 milliamperes. Again, the values substituted for these quantities were not given, but I'll show it to you later. And after that, because we already know the IR and the IZ max is given, we can subtract our IZ max from the IR. If you will go back to the previous slide, the IZM was given as 32 milliamperes. So if you subtract 40, or you divide 40 by, if you subtract 40 milliamperes minus the 32 milliamperes here, we will be getting 8 milliamperes. And of course, we can also calculate the RL max by dividing VZ divided by IL min. We used here Ohm's law, and we will be getting 1.25 kilo ohms. So to represent the what happened, if you can see here, the voltage 10 volts will start to be 10 volts if you use a resistance RL of 250 ohms up to 1.25 kilo ohms. So there will be a constant VL here. Now, this means that the minimum RL, or RL minimum, will be 250 ohms, and the RL maximum is 1.25 kilo ohms. And this will be the range of RL which is necessary as required by the question. And in terms of the current, we calculated the IL min is 8 milliamperes, and the IL max, which will be the IR, is equal to 40 milliamperes here. So as you can see, this is how we calculated the values for the required minimum and maximum ranges of the load resistor and the load current range. Now, just to show it to you again by handwritten calculations, this is the situation that we have the VI 50 volts, 1 kilo ohm R, IZ max 32 milliampere, VZ 10 volts, and the RL is also 10 volts. Now, in the calculations here, let me remove this first. In the calculation of RL min, you will notice that the R is multiplied by VZ over VI minus VZ. And taking this formula into account, we will be getting 1 kilo ohm R and the VZ of 10 volts, and the subtraction of 50 minus 10 volts will be equal to 40 volts. Take note that the VZ is 10 and the input voltage is 50. So we will be getting 1 kilo ohm multiplied by 10 volts divided by 40 volts, and we will be canceling the unit for the volt over volt, and we will have remaining unit of ohm or ohms. And finally, the RL min will really be 250 ohms. In the case of VR, so the VR will be taken from VI minus VZ. So 50 volts minus 10 will be 40 volts. So VR will be equal to 40 volts. For IR, Ohm's law, again, V over R, or VR over R, we got 40 volts from the previous calculation here at the top, divided by 1 kilo ohm. Take note that you may change the kilo ohms to ohm. So 1 kilo ohm here becomes 1000 ohms. So when you divide 40 volts divided by 1000 ohms, we will be getting 0.04 amperes. Take note of this because so many people, students, and sometimes even electronics engineers or whatever, may forget to put the unit, and this is very important to put. So if you want, you can convert it to milliamperes by simply multiplying zero point zero 0.04 amperes or ampere to 1000. So we will be getting 40 milliamperes. Now that we got the VR and the IR and the RL min, the remaining things to do is to calculate for RL max, which is VZ over IL. You will notice that I still use here Ohm's law. So R equals V over I. And because we want the RL max, we have to divide it by the smallest possible IL, which is the IL min. So if you want the RL max, use the IL min in your divisor. And if you want the RL min, you can use here the IL max as well. So RL max is equal to 10 volts divided by 8 milliampere. Remember that volt divided by milliampere will be producing uh, kilo ohm. So if you want, you can change the 8 milliampere first to ampere by dividing it by 1000. So we will get 0.008 amperes and we will get 1250 ohms. So take note, this is ohms. And if you convert it to kilo ohms, you have to divide it by 1000. So we will get 1.25 kilo ohms. For the IL minimum, you can subtract the IZ maximum from IR. So the IZ maximum is given as 32 milliampere subtracted from 40. We got IL minimum of 8 milliamperes. And if you want, you can do the IL max by dividing VZ over RL min, and that will be 10 volts divided by 250 ohms. You will be getting 0.04 ampere, and therefore the IL maximum will become 40 milliamperes. We got 40 milliamperes by multiplying 1000 to zero point zero 0.04 amperes. There you go. This is how to determine the circuit values necessary to be able to get 10 volts 10 volts Zener voltage. So let's move on with about the impedance or impedance. By theory, the impedance of a circuit is calculated or measured in ohms, and this is represented by the letter Z. The term impedance is used to include both inductive and capacitive reactance and resistance because all three are forms of opposition to the flow of current. I will assume that you already know what is a reactance, capacitive reactance, and resistance here because our topic now will be focused on the impedance of the Zener diode. So basically, by Ohm's law, the voltage is equal to the current multiply to the Zener, the impedance. Okay, the impedance. So voltage equals current multiplied by impedance. But for Zener diodes, the VZ is equal to IZ multiplied by ZZ. So Zener voltage is the product of the Zener current and the Zener impedance. I'm talking about this because we will be discussing about impedance of the Zener diode on the next few slides. So again, the Zener impedance may be written as ZZ, and this is the equivalent series resistance of a Zener diode when it is conducting current. So it's clear that this is what we call the series resistance of a Zener diode, and we call it Zener impedance. So the unit of the Zener impedance will also be ohms. Now it is calculated by finding out the changes or the change of the Zener voltage, and this will be represented in our calculation by the triangle here or the delta VZ. And this occurs as a result of a very small change in the Zener current. And we will also call it as delta IZ. So the delta VZ refers to the change of Zener voltage, and the delta IZ refers to the change in the Zener current. Now, the Zener impedance ZZ should ideally be zero, but in reality, a Zener diode has some impedance. So, looking at on this figure in the about determining the Zener impedance, you will see here 19 milliampere along the reverse current IR. This is the 19 milliampere. Let's take this as one of the Zener currents, 19 milliampere, and there's another Zener current here, which is 21 milliamperes. Therefore, to get the delta IZ, all you have to do is to get the difference between the 21 milliamperes and the 19. And of course, if you subtract 21 milliampere by 19 milliampere, you will be getting the answer there. And of course, we have here, let's suppose that this is the IZT, which is equal to 20 milliampere. Okay, and somewhere along here, we have the IZ max. And at the beginning of the VZ, this is where we will find the IZK, but it was not shown anymore in this figure. Now, again, to get the impedance, all you have to do is to divide the voltage by the current. But this particular example, we have to find the changes in the VZ and then divide it with the changes in the IZ in order to get the ZZ. So this is how we will be able to get the value of the impedance of our Zener diode. Again, the impedance is the calculation of the change of the Zener voltage that occurs as a result of the change in the Zener current. That's why it's clear here that we are dividing VZ, delta VZ by delta IZ. Now, it's better if we have the exact calculation that will be occurring later on. So let's move on with the Zener equivalent circuit. So if this is your Zener diode, we can imagine that inside the Zener diode, there will be a resistor that represents the impedance, or there will be an impedance and there will be an internal VZ. So the ideal Zener diode will have no impedance, and therefore the ZZ will be zero. And for the practical diode also, the ZZ is not zero, but this will be greater than zero. In other words, there will be an impedance for a real diode or a practical diode. But theoretically, if we are using ideal diode, then that will be equal to zero. And this current, which is going in the opposite way, this is what we call as the reverse current or IR. Now, the about the Zener reduction of ripple voltage, uh, if you will remember, the ripple is possible to happen in the rectifier circuits, and even if you put a capacitor, there will still be a much less fluctuation of voltages, but there will still be a ripple. In the case of the Zener, we can reduce the ripple voltage in the Zener by using considering the ZZ and the VZ of our example here. So to calculate for the VR out, we can use ZZ parallel to RL, and then ZZ parallel to RL. So as you can see here, Zener uh, the Zener impedance is parallel to the RL. And of course, we can assume that the Z or the impedance of the Zener is not having any reactance or reactance here. So the Z is considered as the internal resistance of our diode. So it will be parallel to RL, and this is how we write it. Now, after that, we have also the value of VR equal to ZZ over ZZ plus RS multiplied by VP. and this is assuming that the ZZ is less than or too much smaller than much smaller than RL. So the VR out is the ripple present at the regulator output. ZZ-RL, parallel combination of ZZ and load resistance. RS is the regulator